Welcome back. In today's class, we want to talk about chemical equilibrium. All right. Now, what are the topics we're going to be looking out for? They are all listed here. So as you can see, the first one is definitions of terms. Now, what is chemical equilibrium? All right. Before I proceed, if today is your first class watching our video or you're coming across our videos for the very first time, please do well to hit the subscribe button to encourage us to do more videos.
First topic, definition of terms. Features of equilibrium.
Right. So what is the definition of chemical? How can we define chemical equilibrium? Please put down. Chemical equilibrium can be defined as the state in which the rate of the forward reaction is equals to the rate of the backward reaction. Now, what are the features of chemical equilibrium? Number one feature is that it has to be reversible. It has to be reversible. For something to be reversible, we have to see this arrow. Now, if you notice, for example, if I have something like this, now the left hand side of this arrow is a reactant and the right hand side of this arrow is a product. So if you notice, the two arrows, they are equal in length, which means the rate at which this one is going forward is equal to the rate at which this guy is going backward. Class, a reaction that is in equilibrium cannot be expressed like this. This is not equilibrium, no, because the rate of the forward obviously is not the same thing as the rate of the backward. Right? In as much as this reaction is reversible, but is not in a state of chemical, it's not in a state of equilibrium because this reaction tends more forward than backward. Please take note of that. If you're writing a system in equilibrium, this arrow, both of them has to be equal. All right. Now, what is the second feature? Remember we said the first feature of the reaction that is in equilibrium is that it is reversible. The second feature is that it is dynamic. Now, when something is dynamic, it simply means that it is in constant motion, right? The forward is moving, this guy is moving to the forward, while this forward is moving to the backward. They are in constant motion. Do you understand? So that's what we mean by dynamic.
Second topic, equilibrium constant Kc and its expression.
So the next one we're going to be looking out for is equilibrium constant. Now, it is important for me to state this, that for any chemical reaction that is in equilibrium, right, there is always bound to be equilibrium constant. Now, once you see a chemical reaction that has these two head arrows, these two double head arrows, right, it simply means that that reaction is in equilibrium. And once a reaction is in equilibrium, there is bound to be equilibrium constant. There is bound to be an equilibrium constant once a reaction is at equilibrium. All right. So first thing first, what is the equilibrium constant? Equilibrium constant has a symbol of Kc. This C stands for concentration. Now, equilibrium constant can be defined as the ratio of the concentration of the product to that of the reactant, each raised to their coefficient. I repeat, equilibrium constant Kc can be defined as the ratio of the concentration of the product to that of the reactant, each raised to their coefficient, their respective coefficients. Now let's say, for example, I have a reaction A plus B giving me C, and I am asked to write the equilibrium constant expression for this reaction. Now, what would that give me? Now, we say Kc, class, ratio. Once they say ratio in mathematics means fraction. So when they say the ratio of the concentration of the product, now how do we know the product? The substance that is always at the right hand side of this arrow is always the product. So C and D are the products, whereas the substance at the left hand side are the reactants. A and B are the reactants in this case. All right. So the concentration of C, we are going to use a square bracket to denote concentration. So this is going to be this C, right? This small letter C is the coefficient, stoichiometric coefficient. So you put your line. This C, the concentration, we're going to use square brackets. Remember, this square bracket stands for concentration. Concentration of C raised to the coefficient of this C, which is small letter C, times the concentration of this D raised to small letter d, which is the coefficient, all over the reactant, because these are the products and this is the reactant. So it's the concentration of the ratio of the concentration of the product, which is this, all over that of the reactant. So we say A, B. Now, look at this reaction we gave earlier. Now, this reaction contains 4 species, 2 reactants and 2 products. What if in a case where we have just a single reactant and a product, what would be the equilibrium constant expression? So if I am to write the equilibrium constant of this guy, this is simply going to be Kc equals to, the product is just only one product, which is B. So this is going to be concentration of B all over concentration of A. All right, so what we just did now is to write equilibrium constant expression now for a hypothetic equations or reactions. Now I'm going to be giving us a real reaction for us to attempt or for us to see how we can write equilibrium constant for real reactions. So we have the following example. All right, so we have this. Now let's look at these two reactions. Imagine you're asked to write the equilibrium constant expression for this. So this is basically what we're going to do. Kc, the product of this reaction is ammonia. So we say ammonia, concentration of ammonia, we use square brackets. What is the coefficient of ammonia? 2. All over that of the reactant, the concentration of this guy we have. What is the concentration of nitrogen? 1 times, you are not going to write the 1 because it's 1 times. That of hydrogen is H2. What is the coefficient of hydrogen? 3. So that is equilibrium constant expression for this reaction. Now, let's write equilibrium constant for this second reaction. So this becomes Kc equals to, the product of this reaction is ammonia. This square bracket stands for concentration. Remember, Kc, this is concentration equilibrium constant. We are writing equilibrium constant in terms of concentration. However, we have equilibrium constant in terms of pressure. We're going to talk about that later. But if they did not mention which of the equilibrium which of them you're asked to write, if they just say give the equilibrium constant expression, please, you should always write it in terms of concentration, right? Unless they asked you to give the equilibrium constant in terms of partial pressure. That is only when you're going to use that of partial pressure. All right. So let's continue. Concentration of ammonia, NH3. The coefficient of ammonia is 2/3. All over reactants, N2. The coefficient of ammonia is 2/3. That's why we have 2/3 here. All over that of nitrogen, the coefficient of nitrogen here is 1/3 times H2. The coefficient of hydrogen here is 1, so that is why we are not going to put 1 here. So you can see how we have written equilibrium constant expression for the individual reactions. So the next thing we're going to do now, I believe that if I should give you any reaction at all, you can actually, based on what we have done now, write your own equilibrium constant expression.
Next, calculation of Kc of one reaction, using Kc of another reaction.
What we want to treat now is calculation of the equilibrium constant of a reaction using equilibrium constant of another reaction. What are we trying to achieve here? I'll give us an example. Let's say, for example, we have we have A, um, let's say we have N2 plus this, we have 2NH3, Kc equals 2.0. And the question goes as follows. Calculate the Kc for the reaction below. Now, in this particular type of calculation, now I've used this question to, explain. This three question covers almost all the areas question can come. We have three scenarios here. Now, remember we said the subheading here says calculation of equilibrium constants of a reaction using the equilibrium constant of another reaction. So in this particular illustration, they gave us this reaction, which I'll call the original reaction or equation 1. And in this case, they gave me the equilibrium constant of this to be 2.0. And then I'm asked to use this reaction and its equilibrium constant to find the equilibrium constant of this, and this. So that corresponds to this subheading that says calculation of equilibrium constant of a reaction using that of another reaction. So in this case, we are going to be solving for the equilibrium constant of A using that of this. We're going to also solve for that of B using that of this. And we're also going to solve for that of C using that of this. Okay, so let's start with the first one. But one thing I would like to let us know is that, remember, when I was actually giving us relationship or expression of equilibrium constant, I told us that you can relate equilibrium constant of two reactions that have same chemical species. If you noticed, this reaction that they gave us the equilibrium constant contains the same chemical species as these three. Chemical species simply means the substance contained in the equation. It may not necessarily be on the same side. They may not necessarily be the same number of moles. But if you noticed, this guy has nitrogen, hydrogen, and ammonia. And all these three guys have nitrogen, hydrogen, and ammonia. The only difference is that their sides may differ or their moles may differ. However, they contain same chemical species. All right, so let's start. I'll say solution for the first one. So let's say I'll say original equation, which is this guy. We have N2 plus this, giving us 2NH3. So we have Kc here equals to 2.0. Class, let's solve for the A. Now, equation A is 2NH3 giving us N2 plus 3H2. So let's call this guy A. Now let's put a subscript A to denote this equation. Now class, look up. What is the relationship between the equation, the original equation, and this equation? Class, listen. Why do I call this guy original? Because it is the equation that they gave us the equilibrium constant. All right. So this other equation, the equilibrium constant of this equation will be solved using that of the original equation. So let's look at the relationship between the original and equation A. Class, if you noticed, the only difference between this original equation and equation A is that this original equation, you will have to reverse this original equation to get this. Remember, this is what you're asked to find. So on no account should you actually adjust what you're asked to find. No. what you should be adjusting is what was given to you, right? Because I'm asked to find this. So basically, I'm going to ask myself, what can I do to this equation that was given to me to use to find this? Because the one that they gave us, the equilibrium constant, is the one you are going to use to find these individual guys. So on no account should you tamper with these individuals. You're going to use them the same way it is given to you. However, the one you're going to tamper with is the original equation that has equilibrium constant. So ask yourself, what can you do to this original equation here to give you this equation A? Good question. So I'll say reversing original equation will give equation A. Now, what do we mean by reversing? If you bring what we have on the product side and bring it to the left, and bring what we have on the reactant side and take it to the right, that is what we mean reversing. So if you reverse this equation, this original equation, you're going to have this, right? Class, anytime equation is reversed, right? Anytime equation is reversed, the equilibrium constant will always be reciprocal of what it was initially. Now, just follow me. Let me explain something. So we say for us to get equation A, we're going to reverse original equation, because if you reverse this original equation, you're going to get this equation A. So how do we now get the equilibrium constant of equation A? So I'll say equilibrium constant of equation A will be equals to, remember I said, once you reverse an equation, the equilibrium constant becomes the reciprocal of what it was initially. Right? So we are trying to get this equation, equilibrium constant of this equation, using this. Now this they gave us to be 2.0. So if I reverse this equation, I will get this. So that means once I reverse this original equation, I'll get this equation A. So for me to get the equilibrium constant of equation A, I am going to take the reciprocal of the original equation. Reciprocal means 1 all over. So the equilibrium constant of equation A would be reciprocal of equilibrium constant of original equation. Why? Because this original equation, when you reverse, you're going to get equation A. So therefore, this becomes equals to 1 all over 2, because this Kc original is 2.0. So you say 1 all over 2.0, which is equals to 0.5. So that is how we got equilibrium constant of A using that of the original equation. So let's look at the second, okay? Let's look at the second question. We say solution for the, now remember our original was given to us to be N2 plus 3H2 into 2NH3. We have Kc equals to 2.0. So they are asking me to, use this guy to find B, because we've done for that of A. So I'll say equation B is 1 all over 3 N2 plus H2 into 2 all over 3 NH3. So we have Kc equals to question mark. Class, look up. Now, remember I told us that anytime you're given two equations, one of them with equilibrium constants given and one of them equilibrium constants not given, you're going to use the equation that the equilibrium constant was given to you to find that of the one that equilibrium constant was not given to you. So to cut the whole story short, look at this overall equation. What can be done to this overall equation for me to get equation B? It's very simple. Let's start with just start with one substance. I will start with the reactant, N2. In the overall equation, nitrogen is 1, whereas in this equation B that I'm asked to find its equilibrium constant, Nitrogen has a ratio, stoichiometric coefficient of 1 over 3. So you ask yourself, what can I multiply with 1 so that I can get 1 over 3? Remember, you're not to adjust anything in this equation that you're asked to find its equilibrium constant. But instead, you're going to ask yourself, what can be done to the equation that the equilibrium constant was given to you? What can be done to the equation that the equilibrium constant was given to you so that you can get the one you're asked to find, right? In this first instance, we have to reverse this equation. But in this second case, if you noticed, there is nothing to reverse. Both of them have the same side. Nitrogen in the overall equation is on the reactant side. Nitrogen on this equation is on the reactant side. Hydrogen reactant, hydrogen is reactant. Ammonia product, ammonia product. The only difference is their mole ratio or their stoichiometric coefficient. So what can be done to this overall equation so that its coefficients will be the same as equation B? So look up. If I multiply this nitrogen with 1 over 3, I'll have 1 over 3. So because of this singular fact that if you multiply high nitrogen with 1 over 3, I'll have this guy. I will now say multiply this entire equation by 1 over 3. Or if you don't want to use nitrogen, you can use any of these species. You can use this guy. Now, hydrogen in the overall equation, in this original equation is 3, whereas hydrogen in this equation B is 1. So you ask yourself, what can I multiply with 3 to give me 1? The answer is 1 over 3. So if you multiply 3 by 1 with 1 over 3, you're going to get 1. So because of that, we'll say if you multiply this original equation with 1 over 3, you're going to get equation B. So therefore, multiply original equation by 1 over 3 to get equation B. All right. So you now say 1 over 3. Now the original equation was N2 plus 3H2 Now, you don't really have to do this. No, I'm just doing this to extend this. You don't really have to do this. Once you've identified that, you're going to multiply this overall equation, this original equation by 1 over 3, right? You can just go ahead and let me just show something. If you do this, 1 over 3 times 1 becomes 1 over 3 N2 plus 1 over 3 times 3 is 1. 1 over 3 times 2 is 2 over 3. So as you can see, multiplying this original equation by 1 over 3 gives us equation B that we are asked to find. So I'll now say equilibrium constant class. Anytime you multiply an equation by a factor, anytime an equation is equilibrium reaction is multiplied by a factor class, you're not going to multiply the equilibrium constant by that factor. No. When it comes to equilibrium constant, whatever you use to multiply the reaction, you're going to raise it as a power on the equilibrium constant. So since we used 1 over 3 to multiply this equation so as to get this, equilibrium constant of this equation B will now be equals to equilibrium constant of the equation, the original equation, all raised to the power of 1 over 3. Why did I say raised to the power of 1 over 3? Because we multiplied original equation by 1 over 3 to get this equation B. All right. So this equation B now, for us to get the equilibrium constant of this equation B, which is what we are asked to find, right? Whatever the equilibrium constant of this original equation was, I'll raise it by the factor I use in multiplying it. And the factor I use in multiplying this guy to give me this was 1 over 3. So the Kc of the B, which is this equation, will be the Kc of the original raised to the power of 1 over 3 because the original equation was multiplied by 1 over 3 to get equation B. So this becomes 2 into 1 over 3. 3 is 1.259, which is approximately 1.26. So that is how we got the KB, the KC of the B. All right. So let's look at the the third example. So the original equation is already on the board. So equation C is 2. Please, this is meant to be 2 over 3. Please just make that necessary correction. This is meant to be 2 over 3. So we'll come here, we'll say 2 over 3 NH3 giving us 1 over 3 N2 plus H2. All right. So if you look at this question here, they are asking me to find the equilibrium constant of this equation C using equilibrium constant of the original equation. So how do we go about this? First thing first, you ask yourself, what is the relationship between the equilibrium constant with a known equilibrium reaction with a known constant and the one without a known constant? Now look up. Now, the relationship between this and this is the first two relationship we did. If you look up, this reaction first is reverse. If you reverse this original equation first, because if you notice in the original equation, ammonia is on the product side, whereas in this equation C that we are asked to find the equilibrium constant, ammonia is on the reactant side. So first thing first, you reverse original equation. When you reverse this original equation, now look at this. First, reverse original. Now just follow me. When you reverse this original, this is what we are going to have. 2, reversing simply means whatever was on the right, bring it to the left. Whatever was on the left, take it to the right. So here, the right hand side had ammonia, 2 moles. So when you reverse this original, this becomes the ammonia now comes to the left. And what was at the left goes to the right. But then you realize that after reversing this equation, it is still not giving us what we need here in this equation C, right? But you can see that first, it has brought ammonia to the left, which corresponds to this ammonia in equation C. It has taken nitrogen to the right, which corresponds to this nitrogen here. It has also taken hydrogen to the right, which corresponds to this. However, their moles are not the same. All right, so the next thing you're going to do here is you ask yourself, what can I do to this equation, this original that I have reversed? Because two things will be done to this original equation to make it look like this. First, we have reversed this equation. That means we have brought what was initially on the right to the left, but the mole is not still corresponding. So now ask yourself, this is equation C, where I am heading to. This is my final destination, but what I have is 2. So what can I multiply with 2 to give me 2 over 3? You ask yourself, what can be multiplied with 2 so I can get 2 over 3 for this ammonia? Whatever I will multiply with 2 to give me 1 over 3, right? If I multiply that with this entire equation, I'll have this. So if you multiply 2 by 1 over 3, you're going to have 2 over 3. So you say, second, multiply through by 1 over 3. Now when you do that, 2 times 1 over 3 is 2 over 3. So this becomes 2 over 3. There is 1 here. 1 times 1 over 3 is 1 over 3. 3 times 1 over 3 is going to be 1, which corresponds to what we have here. So if you look at this is now what we have here as equation C. But then 2 things were done to this original equation. First, you reverse. Second, you multiply. All right. So this is now what I will say. To get Kc of equation C, which is this guy, right? Kc C will be equals to class. Whatever things we did to this original equation, right? We are going to do it to this equilibrium constant to be able to get the equilibrium constant of this equation C. Remember, two things were done to this original equation, right, to arrive at this. So since we did 2 things to this equation to arrive at this answer, we also need to do 2 things to this equilibrium constant to help us arrive at this. So I will say equilibrium constant of this equation C, which is this, would be equals to, what was the first thing we did to this original equation? You reversed, right? Remember, once you reverse an equation, equilibrium constant will now become the reciprocal. So I will say equilibrium constant of these guys, the first step was reverse. So this becomes 1 all over Kc original. But we did not just reverse, we are having 1 all over this because we had reversed this equation. Remember, anytime you reverse equation, equilibrium constant becomes the reciprocal of what it was initially. So if I reverse this equation, the new equilibrium constant of the reversed equation will be 1 all over what it was. And remember, we are heading towards this equation. So for us to move from this equation to this, 2 things were done to this equation. So for us to get equilibrium constant of this, 2 things will be done to this equilibrium constant. So the first will be, you take the reciprocal of this because this equation was reversed. Secondly, we are going to raise the everything here by 1 over 3. Why? Because we multiply this same guy by 1 over 3 to get this. Kc original that was given to us is 2.0. This is raised to the power of 1 over 3. 0.79. This has, if you actually watch this video, you can replay it as many times as possible, right? Do not forget that this video is a full course package, right? If you actually subscribe, or if you actually buy this course, Chem 131 full course, right, you have access to the video, right, all the topics. Not just that, you have access to the material because I have a well detailed documented PDF material in form of ebook. All these points are listed, so you could imagine you read the material before watching the video. Oh, trust me, this will be a walkover for you. Even without reading the material, this is still a walkover. But now imagine if you read the material. So that is why we had to make it a combo package, right? You buy the course contains the ebook material, right? Each topic in Chem 132, well detailed, explained with definitions and terms inside of them. We have a full video for each topic explained, right? That course package also have past questions, right, from the recent year till, let's say, 7-8 years back. It has full past question. Not just that, right? Your textbook exercises, those exercises, I solve them as well, because you realize that in the middle of the semester, they will give you guys assignments or tests, and all might come from the textbook exercise. So instead of you to start running helter-skelter, you can just say, oh, okay, fine, Dale's already solved all of this. You can just check your course package and pick the exercise questions and solve. And then you make life so easy and learning so smooth for you, right? So if you have not bought our course, please go to our website, www.delzischolarsgroup.com, and get a copy of your course, right? Once you do that, definitely you get across to us on WhatsApp. All right, everything is already programmed. You get across to us on WhatsApp, we add it to our group, and then weekends we have a class for us to discuss, and then you can ask questions if you have, because we're going to be having face-to-face conversation. All right, thank you. So we have another question here, guys. And the question says, given the following, please, these square brackets stands for concentration. Given that concentration of ammonia is 3.1 times 10 raised to the power of minus 2, and that of nitrogen is 8.5 times 10 raised to the power of minus 2, and that of hydrogen is 3.1 times 10 raised to the power of minus 3. The question says, calculate the equilibrium constant for these two reactions. So basically, if you noticed, they didn't give us any of these equilibrium constants. However, they gave us the concentration of the species. So this is what I'm going to do. You can decide to, substitute for each of them, but I'm going to do this. I'll actually substitute for the first equation. Whatever answer I'm going to get, I'll use, the pattern we've been using to get the second one. So I'll say first one, solution. Let's say solution. For the first one, for this first equation, I'll first of all write the equilibrium constant expression for this, so that I will now insert those concentrations to get the answer, right? So this becomes Kc for the first reaction. This is concentration of the products. The product in this case is ammonia. Now raise to the power of the coefficient. Now this is raised to the power of 2 all over concentration of N2 raised to the power of 1. The coefficient of N2 is 1. And then, okay, so once you are done with this, the next thing we are going to do is to start inserting the values. Ammonia is given to us to be 3.1 times 10 raised to the power of minus 2 all squared. Nitrogen is 8.5 times 10 raised to the power of minus 2. This is nitrogen. Now, we are not going to raise it to anything because that's 1 times hydrogen is 3.1 times 10 raised to the power of minus 3 all cube. Now, when you press your calculator, Kc for the first reaction will now become 3.8 times 10 raised to the power of 5. So that is the Kc for that reaction, for this first one. But look at what I'm going to do here. To solve for the second one, there are two ways to solve for the second guy. It's either we'll actually follow the same pattern, right? Writing the equilibrium constant expression for this, and then start substituting the values. Or I'll now say, since I now know the equilibrium constant of this guy to be Kc equals to 3.8 times 10 raised to the power of 5. I can now use the concept we used previously, calculating of equilibrium constant of a new reaction when one is given to us. Now, if you look at this, they contain the same chemical species. The only difference is that they are the reverse of each other. All right. So for me to solve for the B part, I'll say equation B is obtained, right? If you reverse this equation A, you're going to get equation B. Now, why are we reversing this guy now? Because we now know the equilibrium constant of the first one. So we want to use the first one to solve that of the second guy, right? So we now say equation B is obtained from, or is obtained by, reversing. We can say it can be obtained by reversing equation A. So if you reverse equation A, you're going to have equation B. So therefore, remember, if I reverse equation A to get equation B, it means that equilibrium constant of this equation B will now be the reciprocal of the equilibrium constant of equation A, because We reversed equation A to get equation B. So this becomes, so therefore, KCB becomes 1 all over KCA. I repeat, why did we do that? Now, we've known this one here by virtue of carrying out that calculation. Now, remember the concept I said, once you know equilibrium constant of a reaction, you can use it to solve for that of the second guy. Now, if you look at this, if I reverse this equation 1 or equation A, I'll get equation B. So therefore, equilibrium constant of equation B will be the reciprocal of this equilibrium constant of equation A. So when you do that, this becomes 1 all over 3.8 times 10 raised to the power of 5. And this is equals to this. Now, you can see the side if you're not comfortable with that pattern, you can say, okay, let me go with writing equilibrium constant expression for this guy. So you say N2 H2. This is alternatively. Now, alternatively, if you're not comfortable with that, you can say, okay, let's solve for this one directly. We're still going to have the same answer here. So say, what is the value of nitrogen? 8.5 times 10 raised to the power of minus 2. What's the value of hydrogen? 3.1 times 10 to the power of minus 3, all raised to the power of 3. Now, ammonia is 3.1 times 10 to the power of minus 2, all raised to the power of 2. Class, when you press your calculator, you're going to still get 2.635 times 10 raised to the power of 6. All right, so now you tell me which of these two process of solving for the B would you prefer? Well, as for me, I'll prefer this because once I've gotten the first one, I'll just use my calculator to get the second one straight. We have an example here, right? If you look at this question here, they said given that the concentration equilibrium constant Kc, recall I told us that we have equilibrium constant written in terms of concentration. We also have the one written in terms of partial pressure. But the one of concentration predominates. You should only write the one of partial pressure if it is solely indicated or stated. All right. Otherwise, you should write that of the Kc. Given that the concentration equilibrium constant Kc at a certain temperature is 0.52 for this reaction, write an expression for and calculate equilibrium constant Kc for the equilibrium reaction. So they're asking us two questions here. First, you have to write the expression for this, which I'm going to show us. And secondly, you have to solve for the equilibrium constant. Now, all right, so let's start. I'll say solution for equilibrium constant expression. I'll say expression for Kc. Now let's write equilibrium constant expression for this particular guy. So we'll say Kc is equals to, now the product of this reaction, recall that equilibrium constant is the ratio of the concentration of the product to that of the reactant, each raised to their coefficient. All right. So what is the expression? What is the concentration of this ammonia? You put it in a square bracket, NH3. Now the coefficient of ammonia here is 8 all over 3. Now this is divided by nitrogen. The coefficient of nitrogen is 4 over 3 times concentration of hydrogen, right? The coefficient of this guy is 4. So having done this, we have written equilibrium constant expression for this reaction. Now, they are asking us to solve Kc of this reaction. So I'll say II Kc of the new equation. Now, this is what you're simply going to the class. Recall in the previous illustration, or in the previous section, we said that if they give you equilibrium constant of a reaction, you can use it to solve equilibrium constant of another reaction, provided that they contain the same chemical species, right? Now, this guy contains nitrogen, hydrogen, and ammonia. And of course, this guy also contains nitrogen, hydrogen, and ammonia. The only difference is their mole, all right? So, they gave us equilibrium constant for this equation to be 0.52. So, we'll say Kc for this is 0.52. So let's solve for that of this guy. Class, look up. What can be done, or what will I do to this equation that the equilibrium constant was given to be able for us to get this equation that we are asked to find the equilibrium constant? Whatever we are going to do to this equation, right, we are going to do it to this equilibrium constant. And obviously, equilibrium constant of this, we are going to get it through that process. So look up. Now, if I should multiply this equation here by 4 over 3, if I should multiply original equation by 4 over 3, I'll get this. Because if you say this is 1 here, 4 over 3 times 1 is 4 over 3. 4 over 3 times 3 is 4. Because when you say 4 over 3 times 3 is 4, which is what we have here, 4 over 3 times 2 is 8 over 3. So in other words, so therefore, for us to get equilibrium constant of this reaction, class, listen. We are going to first of all ask ourselves, what can we do to this equation now to get this? We can see that we are going to multiply this equation by 4 over 3. So therefore, the equilibrium constant of this reaction will be the equilibrium constant of this raised to the power of 4 over 3, because when you multiply this equation by 4 over 3, you're going to get this, right? So now say equilibrium constant of this new reaction will be equilibrium constant of the original reaction, which is this guy, all raised to the power of 4 over 3. I repeat, why did we say 4 over 3? Because when you multiply this equation by 4 over 3, you get this. So for you to now get equilibrium constant of this, you now ask yourself, what did we do to this equation to get this? We'll multiply this equation by 4 over 3. So for us to get equilibrium constant of this reaction, we'll raise this equilibrium constant by that same factor that we used to multiply this, which is 4 over 3. All right? So this now becomes 0.52 raised to the power of 4 over 3. So we now have 0.52 raised to the power of 4 divided by 3. So the answer to this now becomes equals to 0.42. So Kc of the new reaction, which is this, is 0.42. So it's as simple as that. So if you have any question, drop it on the comment or drop it on our group chat, the paid group for this course. All right.
Fourth topic, multiple equilibria.
We have another topic here, multiple equilibria, right? As the name implies, multiple. So let's look at what we have here. We said in multiple equilibria. So I said here, like in multiple equilibria, I mean more than one equilibrium expression and constant is given, right? Like in this case now, we have two equilibrium reaction, right? Now from their data and value, a new equilibrium constant is calculated. This is similar to that of Hess law. So let's say, for example, they said we have this equilibrium constant for this guy to be 2.0, and we have that of this guy to be 3.0. And then they gave me this equation 1, this first equilibrium reaction, and then they gave me its equilibrium constant. They gave me the second equilibrium reaction, and of course its equilibrium constant. And now the question says we should find the equilibrium constant of this reaction. Now I purposely wrote overall reaction here, because in exams or anywhere they won't use overall reaction, and I'm only telling us, or I'm trying to make us understand that this is the one you're asked to find now using these two individual guides. Now, what is the concept behind this? The concept behind this is that you're to rearrange this equation here and make it look like this, so that at the end of the day, whatever is not present in this equation will be cancelled out. Now let's have a look. In equation 1, class, remember, this is actually where I'm heading to. This is the main equation. This is where I'm heading to. So all my attention should be on this particular overall equation. So I'm going to rearrange these individual equations to make it look like this if it is not looking like that already. So let's look at this equation 1. In equation 1, or from overall equation, there is A on the reactant side. Now let's look up to these two equations. We have A on the reactant side, which correspond 1 mole of A in the overall equation, right? So on the in this individual equation, we have A on the reactant side, 1 mole. Now, coming down to this overall equation again, we have X on the reactant side. So we look up to these two individual equations. We can see X on the reactant side as well. So that means this and this is on the reactant side, which corresponds to this. So I'll come down to this. Overall equation has C on the product side. This equation 1 has C on the product side, which is okay. Overall equation has D on the product side. This guy also have D on the product side. However, if you look at this overall equation, class, there is nothing like B in this overall equation. All right, but we have B in this individual equation. So what are we going to do, class? Any species, right, that is not present in the overall equation, in this case, but it is present in these two individual equations, sometimes they can give us 3, has to be cancelled out. It's a must. It has to be cancelled out. Now, this pattern is very similar to that of Hess law. Hess law in thermochemistry, but we don't want to go into Hess law. So if you look at this, B is not present in this overall equation. So however, or whatever, we're going to cancel out B from this equation. And class, for B to be cancelled out, they must be on opposite side. Opposite side means one of the B has to be on the reactant side and the other B has to be on the product side. Right? Not just that, they must have the same stoichiometric coefficient. Because if I have 2B on the left and I have 1B on the right, this cannot cancel because 2 minus 1 is 1. So for this guy to be able to cancel, we must have 2 on the left, 2 on the right. So that is it. So let's look at this. So I'll say in equation 1, B is on the left hand side. In equation 2, B is on the product side. All right. So when you do that, now let's rewrite this so that you see what I mean. So if you rewrite this guy, we have A plus B giving us C. Our KC for this is 2.0. We have X giving us D plus B. KC for this, let's take 3.0. Now this is the overall equation, right? We've seen that A, okay, overall equation has A, so equation 1 has A. So I put it down. Now this A is taken care of, this equation 1 is taking care of A in the overall equation and C. A and C. And this second equation is taking care of X and D, which is X and D. Now, B is not present in the overall equation, so B has to be cancelled out. All right, I just told us that B has to go. And for B to go, it has to be on opposite side, same amount. All right, so if you look at this, on the reactant side, there is B. On the product side, there is B. So when you cancel out B, you bring down the reaction. We have A plus X. This becomes C plus D. Now, interestingly, this is not what I was asked to find because this is what is here already, right? What I'm asked to find is the equilibrium constant of this reaction, okay? But I cannot just, do whatever I'm going to do to just say, okay, I'm asked to find the equilibrium constant of this reaction. So once I'm able to get this overall equation from this individual, I'll now say over equilibrium constant of the overall reaction will now be equals to Now let's call this guy equation 1 and let's call this guy equation 2. So equilibrium constant of the overall reaction will now be Kc of 1 times Kc of 2. So this becomes 2 times 3 equals to 6. So that is the concept behind multiple equilibria, right? So we're going to be taking some few examples to see how we're going to relate this to real example. So sit back. So we have examples here under multiple equilibria, but the first important question a lot of persons want to ask is that what's the difference between this multiple equilibria calculation and the previous calculations we just completed, where you are asked to use equilibrium constant of one reaction to find out of the other? Class, in multiple equilibria, as the name implies, multiple, they will always give you at least two equations with their constants, and then you'll be asked to use these two of them to find that of the overall. So that's the difference. In multiple equilibria, they might give you three equilibrium expression or reactions with their constants, and then you're asked to use those three to find another equation that will make it up to four equations. So in this case now, we have two equations here already, right? This, and we are asked to use these two to find this. Here we also have two equations. We are asked to use it to find this. Mostly under multiple equilibria, you're most likely going to be seeing two individual equations for you to find one overall. All right, so let's get started. You have to find equilibrium constant for this reaction. So the first thing I'm going to do is that come to this overall equation. What I'm going to do is to rearrange these two equations to make it look like this, or better still, I want to get this overall equation from these two equations here. You understand? So here, this overall equation, I want to get it from these two individual equations. So how do we go about it? First thing first, in the overall equation we have NOCl. So look up through these two equations now. Which of them contains NOCl? The first one. But the NOCl in the first equation is having two moles or two molecules. So we need to reduce this NOCl from two molecules to one to make it look like this. Remember, our aim is to rearrange these individual equations to make it look like the overall. Do you understand? Right. So NOCl is the first one we are dealing with. So there is NOCl in this overall equation at the reactant side. In equation 1, there is NOCl still on the reactant side. All right. There is NOCl still on the reactant side, but the only difference is that in this case now, this NOCl is 2 moles, right? This guy is 1 mole. So basically what we are going to do here is to multiply this by half. What we are going to multiply this entire equation by half so that this that was initially 2 becomes 1. So say multiply equation 1 by 1 over 2. So if you multiply this guy by half, half times 2 is 1. So we have this. All right, so you move down to the product side. Half times this. Now, 1 here, this is 1 over 2 Cl2. Now, if you noticed, in the process of doing this, we've succeeded in taking this NOCl from 2 moles to 1 mole, which corresponds to what we have here. But remember I told us that whatever you're going to do to these individual equations, right? If you multiply an equation by a factor, the equilibrium constant will not be multiplied by that factor, but instead it will be raised by that factor. So here, my K1 here will now be 4.4 times 10 raised to the power of minus 4. Now, this will be raised to the power of half. Why am I saying half? Because we multiplied everything here by half. All right, so I'm going to leave it out here. Later, we're going to do the evaluation. Now, so I've taken care of this. If you notice, this equation 1 took care of NOCl and also took care of Cl2 because in the overall equation, NOCl was 1 mole, whereas NOCl in equation 1 was 2 mole. So by multiplying this guy with half, this guy becomes 1. So if you look at this overall equation, Cl2 is half, but here Cl2 is 1. So by multiplying this guy by half, here becomes half. All right. So let's look at the next one, oxygen. Now, I can choose to say oxygen or I can choose to say NO2 as long as these guys are appearing only once in this individual equation. Oxygen is appearing only in equation 2. NO2 is also appearing only in equation 2. So I can decide to say, okay, fine. Let me use oxygen or let me use NO2. Whichever of them you choose to use, you're still going to be very correct. So, but let's use oxygen. In the overall equation, oxygen is half. Whereas in equation 2, oxygen is half also. So we have half here. We also have half here. Do you understand? So in this case now, this is what you're going to do. We are not going to multiply this equation by anything at all. Nope. We're not going to multiply this guy by anything at all. But instead, we're going to bring down this equation the same way it is. So when you do that, equation 2 remains the same. So this becomes NO plus 1 over 2 O2, giving us NO2. Now our K2 remains 83.3. So having done that, let's get our final equation. Class, this is what we are asked to find. So remember I told us earlier that we're going to use these two equations to get this from it. So we are done with the rearrangement. Next thing we're going to do is that look at this overall equation. Is there anything that is actually present in this overall equation that is not present in this individual equation? Yes, there are. Let's check it out. NO is present in this individual equation, NO, but there is no NO here. So obviously NO has to go. So I think it's only NO. And remember I told us that for a substance to be cancelled out, right? For a substance to be cancelled out, it has to be on the opposite side, same amount. So this NO, 1 mole here, and this NO we have 1 mole. So this cancels this. And of course, when you bring down what we have left, NOCl plus half O2, and then we have NO2 plus 1 over 2 Cl2. Now you notice that we've been able to get the overall equation that was given to us by basically rearranging this particular individual equation. But we are not done. They did not ask us to, to just rearrange and give them this equation. No, the question says determine Kc for this reaction. So the main purpose of we doing all of this was for us to get the Kc, that is the equilibrium constant of this overall reaction. Remember I told us that anytime for equilibrium constants, once you're done rearranging, you're not going to add up those equilibrium constants, you're going to multiply. So we'll say Kc overall will be the multiplication of the equilibrium constants of these individual reactions after rearrangement has been carried out. So this is going to be this K1. Let's put asterisk here because we did something to this equation. That is, we raised this guy by half. But however, this guy we did not do anything, so there's no asterisk. So we say K1 asterisk times K2. We are multiplying, not addition. So in place of K1, you say 4.4 times 10 raised to the power of minus 4 raised to the power of half times 83. This is basically saying square root of this. So this will give us 2.1 times 10 raised to the power of minus 2 times 83.3. Now when you now evaluate everything here, you're now going to have 1.7. So our Kc overall, that is the equilibrium constant of this reaction, is now 1.7. I believe that with this explanation, you can always carry out lots of calculations. Now, so let's look at this. Now, anytime they give you equilibrium reaction, 2 or more equilibrium reactions, and they are constant, and you're asked to find equilibrium constant of a new reaction like this. I already explained the concepts behind this in the previous examples. So basically what we need to do is to rearrange these two individuals equation to be able to get this overall equation. So we need to get this from these two guys. So we're going to rearrange this, and at the end of the day, whatever the equilibrium constant is, we're going to multiply together, not addition. So if you look at, let's start. Let's say solution. If you look at this guy, in the overall equation, we have NO2 on the reactant side. Now look through these two equations here. Which of them contains NO2? The second equation, right? Now, if you look at the second equation, the NO2 that is present here is 2 moles. And in the overall equation, the NO2 is also 2 moles. Remember, our aim is to actually make sure that these individual equations look like the overall equation. So we are using this overall equation as a reference or as a basis upon which we are going to rearrange this guy. So first, this NO2 is on the reactant side and 2 moles. Look through these two equations. Where can we find NO2? Equation 2, still on the reactant side. So for the fact that it is on the reactant side, I'm not going to reverse, right? I'm not going to reverse that guy. So I'm going to bring down this NO2 like that. Why? Because it is on the reactant side, which corresponds to the 1 in the overall equation. And also, the mole is 2 here, which corresponds to the one we have here. So I would say, bring down equation 2. I would say equation 2 remains the same. Equation 2 remains same. Now when you do that, this becomes 2 NO2. All right, you now have 2 NO plus O2. Now if you bring down your equilibrium constant here, we have this. This is 1.1 times 10 raised to the power of minus 5. Recall, we didn't really do anything to this equation, so equilibrium constant remains the same exactly. Now, let's look at the second guy. So we've taken care of this. So the next one is nitrogen. Now, oxygen is actually the third species here, but we're not going to touch oxygen because oxygen is appearing twice in equation 2 and in equation 1. So anytime a species in the overall equation is appearing more than once in the individual equation, we don't touch it. We leave it out. All right, so if you look at this guy, there is N2 here and there is N2 here. But if you notice, in the overall equation, N2 is on the product side, whereas in equation 1, N2 is on the reactant side. So what are we going to do? First thing first, we need to reverse this equation 1 so that this N2 will come to the product side to correspond to the one we have here. But even after reversing this equation, the mole is still half. And we need this mole to be 1 so as to correspond to what we have here. So because of that, two things will be done to this equation 1. First, you need to reverse so that this N2 comes to the product side and correspond to the side of this guy. Secondly, you need to multiply this half by 2 because 2 times half will give us 1. If you multiply 2 with this half, what you're going to get is 1, which is corresponding to what we have here. But you're not just going to multiply just the coefficient of this N2 by 2. Instead, you're going to multiply the entire equation. So like I said, two things will be done to this guy. So this becomes reverse 1 and multiply by 2. So since I'm actually writing it in a board marker where I can clean it off and rewrite new stuff, I'm going to take it step by step. But you that is writing with pen and paper, you don't have to write first and then write the second one. So you need to understand it at once so that you can write a full stop. So when you reverse this guy, reversing simply means whatever is on the reactant side goes to the product. What we have on the product comes to the reactant. All right. So when you reverse this guy, this becomes NO, this 1 over 2 N2 plus 1 over 2 O2. Class, remember, anytime you reverse equation, the equilibrium constant, you have to take the reciprocal of that guy. All right. So I'll say Ki Since I've tampered with it, I'll put an asterisk here to show that it is no longer the same thing as what we have here initially. This becomes equals to 1 all over 4.8 times 10 raised to the power of minus 10. Remember, what we just did here is reversing. So N2 is now on the product side, but then it is not, the mole is not the same thing as what we have here. The mole here is 1, right? This guy is still half. So we need to multiply by 2. That is why I said reverse 1 and multiply by 2. So if you multiply this entire equation by 2, 2 times 1 is 2 here, right? 2 times half is 1, so I'm going to clean this off. 2 times half is 1, so I'm going to clean this off. Remember, in this case now, anytime you multiply an equation by a factor, you're going to raise the equilibrium constant by that factor. So having done that, we are now going to come here and say, this is raised to the power of 2, right? So therefore, let's get our overall equation. Now, this is the overall equation. So for us to get this overall equation, class, look at these two equations here. Whatever is not present in this overall equation has to be cancelled out. All right? NO is not present here, so NO has to go. And for something to be cancelled out, they must appear on both sides same amount. So if you look at this guy, there is NO on the left-hand side, and there is NO on the right-hand side. So this becomes 2 moles here, cancels 2 mole. So you bring down this guy, this becomes 2 NO2, giving us, you bring down your N2. Class, if you notice, there is oxygen here, there is oxygen here. Both of them are on the product side. Anytime a substance, two same substance appears on the same side, you add. When they appear on the opposite side, you subtract, right? If they have the same number of moles, the subtraction turns to cancellation. So this is 1, this is 1. 1 plus 1 is 2. So we have gotten this overall equation, which is this. So what we want to do now is to get the equilibrium constant, because we were not asked for just this equation, we were asked for the equilibrium constant. So I will say Kc of the overall reaction is going to be Kii. Remember, we did not do anything to this equation 2, we just brought it down like that. It will be K2 times this guy. So let's say times. Now, so what is the value here? Kii is 1.1 times 10 raised to the power of minus 5 times this Ki asterisk is 1 divided by 4.8 times 10 raised to the power of minus 10. Why did we say 1 over? Because it was reversed. And that same equation was multiplied by 2, so which is indicated by this. So when you press your calculator, this becomes 4.77 times 10 raised to the power of 13. So the equilibrium constant of the overall reaction, which is what we have here, is equals to 4.77 times 10 raised to the power of 13.
Fifth topic, relationship between Kc and Kp.
Guys, in this episode of Chemical Equilibrium, we want to discuss relationship between Kc and Kp. Now, remember I told us that equilibrium constants can be expressed in two ways, either in concentration or in terms of partial pressure. However, the concentration tends to predominate. So if you're asked to write equilibrium constant expression, right, you should always go with your Kc, that's the concentration equilibrium constant, unless otherwise stated that you should write for Kp. All right. Now, first thing first, equilibrium constant is the ratio of the concentration of the product to that of the reactant, each raised to their coefficient. Now, this definition mostly is for that of concentration, which of course predominates. But what if you're asked for P, like Kp? Now, Kc is concentration equilibrium constant, and then Kp is partial pressure. Now, let's look at this. Let's say, for example, we have A plus B giving us C plus D. Now, my Kc for this reaction will be I believe by now, if you have watched our videos from the first one till now, you should actually know how we arrived at this. And then okay, now this is for concentration equilibrium constant. Now for partial pressure, in place of this concentration, the square bracket you're seeing there stands for concentration. For partial pressure, in place of that concentration, I use capital letter P. All right, so this becomes for Kp we have. So this is partial pressure of C raised to the power of C, partial pressure of D raised to the power of D, partial pressure of A raised to the power of A, partial pressure of B raised to the power of B. So that's the difference between concentration equilibrium constants and partial pressure equilibrium constants. So this is basically how to write expression for concentration equilibrium constant and partial pressure equilibrium constant. Now, let's now look at the relationship between two of them. So the relationship between two of them is Kp now this is a relationship between partial pressure equilibrium constant and concentration equilibrium constant. We already know that Kp is partial pressure equilibrium constant and Kc is concentration. Now what is this R? R here is gas constant, which they can give us to be 0.0821 atm liters per mole per Kelvin, or you can say 8.321 joules per mole per Kelvin. And whichever of this that is given to you, you can make use of it, but most likely you're always going to use this. Okay, now the T here is temperature, and temperature must always be in Kelvin. Now this delta N is difference in moles of gaseous products and reactants. Well, this thing simply means that if they give me something like A plus B because if you're asked to actually carry out this calculation, they must always give you a chemical reaction. Class, anytime they give you a chemical reaction, things you should be looking out for is the state of the reactant and the product. If they give you a case where nothing is written here, right, you can actually assume them to be gas. Now, if one part, if here is liquid, here is a gas, here is solid. Now, those type of equilibrium, we call them heterogeneous. We're coming to that. We call them heterogeneous because all the states are not the same. But in the cases like this, where all the states are the same, we call it homogeneous. So all this while, we have been carrying out calculation for homogeneous, right? Heterogeneous is just something we need to know just in case. Because if you look at this, we said N, delta N is difference. That's the product minus the reactant. But we emphasized on gaseous product and reactant. So it means that if I want to solve for my N, N will be equals to C plus D, provided that this guy is a gas. It's either it is written as a gas or they will not write it at all. Anytime they don't tend to write the state of a reactant or product, you take it to be gas. So this is minus the product. The mole of the product is C plus D, which is a product. Now the reactant is A plus B. So that is how we are going to get this delta N. Okay, so apart from R, class, apart from R, they might ask you to solve for any of these parameters. They can give you Kc, give you R, give you R, give you T, give you delta N. You have to get it from the reaction. And then you have to solve for the Kp. Or they can ask you to solve for anything at all. There are different ways questions can be asked. Do you understand? So let's take some few examples under this guy. So we have examples here under relationship between Kc and Kp. Now the first question says Kc, that is a concentration equilibrium constant for this ammonia synthesis reaction at 725 Kelvin was found to be 6.5 times 10 to the power of minus 2. Calculate Kp for the reaction under the same condition. How do we go about it? So first thing first, I'll say solution. Now I'll say Kc for this particular reaction is 6.5 times 10 to the power of minus 2. Now the temperature for this reaction is 725 Kelvin. Now they gave us our Kp. We do not know the value of Kp. Do you understand? Now, what else do we need to solve for this guy? They gave us our R, gas constant to be 0.0821 liters atm per mole per Kelvin. Now, we are asked to solve for the Kp. How do we go about it? Recall, I'll say using Kp equals to Kc RT delta N. Now, the delta N here, if you look at this question, this is the reaction, right? They are all in gases. Remember I said it's either they will indicate all the states to be in the same form or in different form, or they will not indicate it at all. So if they indicate all the states, it makes it very easy. So you get to see the one that are gases. Class, you only take the ones that are gases. Anyone that is not a gas, in this case, you ignore that guy. All right. So we said delta N is a difference in the moles of the gaseous product and that of the reactant. So the product in this case is ammonia. And what is the mole here? 2. 2 minus the reactant, we have nitrogen and hydrogen. The mole here, this is 1 and this is 3. So this becomes 1 plus 3 equals to 1 plus 3 is 4. 2 minus 4 is minus 2. So we have gotten our values. So the next thing we're going to do, we say, so therefore, Kp now becomes, anywhere you see Kc, you put 6.5 times 10 raised to the power of minus 2 times our R is 0.0821 times our temperature is 725. Now our delta N is minus 2. So when you do this, you now carry out your calculation. So when you carry out your calculation, this now becomes 1.83 times 10 raised to the power of minus 5. So that is the answer to that first question. Okay? Now, let's solve for the second question. So let's solve for the second question. The second question says, in the reaction, very same reaction as the one we have up here, the equilibrium concentration determined at 725 were this. So they gave us concentration of ammonia to be equals to, this time around, they did not give us the equilibrium constant, concentration equilibrium constant directly. No, So what they did was that they gave us the concentration at equilibrium. So we just need to use this concentration, write expression for this, insert these values, get the Kc, and now use the other formula to get the Kp. So ammonia is 0.095 molar, nitrogen is 1.0 molar, and then hydrogen is 0.5 molar. All right. Now the reaction is N2 plus 3H2 giving us 2NH3. So you now say, you write expression for this Kc is equals to concentration of this raised to the power of 2 N2 raised to the power of 1 H2 raised to the power of 3. So what you just need to do here, you come here, the value for ammonia was 0.95, 0.095, all raised to the power of 2, that's squared. The value for nitrogen is 1.0, and the value for hydrogen is 0.5. So our Kc here now becomes equals to, this is 0.51, and there is 1 here. Our Kc, if you now evaluate this with your calculator, our Kc gave us 0.0. Now we've gotten the value for Kc, but remember, the question says, use the data to calculate the Kc, which we have done at this temperature, and Kp. So once you've gotten Kc using these values, right, you can now say, okay, there is a relationship between Kc and Kp, which is Kp equals to Kc, you complete it. Now, what if they had given us these values in partial pressure? Claire, listen, let me explain this. They gave us these values in concentration. That was why we had to first of all solve for Kc. But what if they had given this value to us as partial pressure? If they had given us this value as partial pressure, class, we would have solved for Kp first and then solve for Kc. And in that case, they would have indicated it here. Kp would have come first before Kc. But since they gave us these values in concentration, so we have to solve for concentration equilibrium constant first, and after which solve for the partial pressure equilibrium constant. Okay, so I'll now say temperature is 725 Kelvin, right? Our R, we already stated it here, 0.0821 liters atm per mole per Kelvin. Right? Now our delta N is very similar to the first one. Right? This is actually the difference in the moles of the gaseous product to that of the gaseous reactant. The gaseous product here is 2. The reactant is 1 and 3. So I'll say 2, which is on the product side, minus reactant side is 1 plus 3. Now 1 plus 3 is 4. 2 minus 4 is minus 2. So therefore, I'll now say Kp equals to Kc RT delta N. Now Kc here is 0.068. Our R is 0.0821 times, what is our temperature? 725 Kelvin. Now this is raised to the power of what? Minus 2. So if you press your calculator, now becomes 1.92 times 10. So this is the value. Our Kp becomes 1.92 times 10 raised to the power of minus 5. All right. So you can see how questions can be asked based on Kp and Kc. So let's look at one other example. We have another question here. They said the equilibrium constant Kc for the reaction how this reaction is different from the previous two reactions. At 2000 degrees Celsius is 4.08 times 10 raised to the power minus 2. At 2000 degrees Celsius is 4.08 times 10 raised to the power minus 2. They now said calculate Kp for the reaction. Now, I gave us this question because I wanted us to understand this beyond the normal, student solving. The previous two examples we did, I just gave us one equation or one reaction, and that one reaction, they gave us the Kc of that reaction, and you're asked to solve for the Kp of that same reaction. But in this case, the equation that they gave us, the Kc, is different from the equation we are asked to solve for the Kp. But if you noticed, this equation that the Kc is given to us has the same chemical species like the one they're asking us to solve for the Kp. So if you could recall, when we started chemical equilibrium, I told us that there are cases where they'll give you equilibrium constants and a reaction, and you're asked to use that to find the equilibrium constant of another reaction. So this is what you're going to do. First, you're going to find, if you notice this equation here is a reverse of this equation, which means if I reverse this equation that the Kc is given to me, I'll get this. So first thing first, I need to get the Kc of this reaction. Once I've gotten the Kc of this reaction, I can now start solving for the Kp of the reaction. Do you understand what I just said now? This equation that we are given the case is not the one we are asked to find for the Kp, right? But they contain the same chemical species. So first of all, I will have to reverse this equation to make it look like this, and then reverse it and multiply it by half so that I can get this one and get the equilibrium constant. So let's proceed. So I'll say first, solution, first, solve Kc for the new equation or reaction. Class, if you look up, this equation that we are asked to find the Kp is not the same as what this guy we are given the Kc. So the first thing we are going to do here is that if you look at this NO, this equation we are asked to find the Kc, the Kp, the NO is on the reactant side, 1 mole. But the one that they gave us, this guy, NO is on the product side, 2 moles. So we need to make this particular one to look like this so that we can get the equilibrium constant for this. In other words, I want to solve for Kc of this guy first. Once I've gotten the Kc of this guy, this is very similar to those previous examples we did before now. So once I've gotten the Kc of this, I can now start talking about solving for the Kp. So how do we get the Kc of this guy? We're going to get the Kc of this guy using this. So let's say Kc of the new equation will be equals to, class, what can be done to this equation now? Okay, let's write out the original equation. So let's say old equation. Now let's call this equation original. Let's call this guy original. N2 plus O2 giving us 2NO. And the Kc of this guy is 4.08 times 10 raised to the power minus 2. And then the new is NO So like I said, remember our final target is not Kc, but we need to get the Kc so that we can use the relationship between Kc and Kp to get the Kp of this reaction. All right, so for us to get the Kc, so let's call this guy new. So the Kc of this new equation will be equals to, class, look up. We are going to use the equation that the equilibrium constant is given to find this. So what can we do to this equation that has the equilibrium constant? What can we do to this equation to get this? Two things. First, in this equation, NO is on the reactant side, in this guy, N is at the product side. So first thing, we have to reverse it. So after reversing this equation, guys, the mole of this guy is 2, while the mole of the one we are looking for is 1. So we need to reduce these 2 moles to 1 mole. And how do we achieve that? By multiplying this equation by half after reversing it. All right, so we are going to reverse this equation so that this NO comes to the left-hand side and correspond to what we have here. And after reversing it, we're going to multiply it by half so that if you multiply half by 2, you're going to get 1. So when you do that, the Kc of this guy will now become 1 all over the Kc of the old guy. Why did we say 1 all over? Because we did reverse. Now, after reversing this guy, right, we multiplied by half. So once that you multiply by half, this equation, this constant, first when you reverse, this constant becomes reciprocal, which is what we did here. When you now multiply by half, this guy now becomes raised to the power of this. All right, so you now say 1 all over 4.08 times 10 raised to the power of minus 2, or raised to the power of half. So Kc new Kc new will now becomes 4.95. Guys, do not forget that we have a course package, Chem 131, Chem 132. So once you buy a course package, the course package comes with a free ebook, number 1, free videos or videos for all the topics for that course, all the topics and all the exercises in the textbook for that particular topic. Past questions, weekends, revision class. So in other words, if you're busy with your practicals, your lectures within the day or during the day, you don't have to stress yourself. During the night or your evening time, or even in the class while you're waiting for your lecturers, instead of it to be discussing with your friends, you can just put on your earpiece and be learning right there in the class. Now, this method or this approach is going to make you go or be ahead of your lecturers and also your fellow students. And as a matter of fact, that is actually the behaviors or the characters of smart and intelligent students, which I believe everyone will be watching this video belongs to that category. Be smart today and make all your A's. All right, so coming back to this, we have succeeded in solving for the Kc of this new equation. All right, so now say NO, this 1 over 2 N2 plus 1 over 2 O2. The Kc of this guy is now equals to 4.95. Remember, this was the same equation we are asked to find the Kp. So we have gotten the Kc now. So we can now say Kp of this guy, question mark. Now, what was the temperature given to us in this equation? You must always give you temperature as long as this relationship is concerned. 2000 degrees Celsius. You must convert it to Kelvin. So this is 2000 plus 273, which is 2273 Kelvin. Okay, now our delta N is equals to, remember, these are all gases. So let me come back here and add gases. This is gas and this is gas. Now, the product of this reaction is N2 and O2, and their mole is half and half. So I will say the mole of the product, we have two products, 1 over 2 plus 1 over 2 minus the mole of the reactant, which is 1, right? So in this case now, this becomes 1, half plus half is 1, 1 minus 1 is equals to 0. So therefore, I'll say Kp, using Kp equals to Kc, RT delta N. So have our Kc in this case is 4.95 times our R. They gave us R to be 0.0 0.821
Yeah, you don't have to bother
times
yourself
our
because
temperature
anything
is
raised to the power of 0 is 1. So
2273.
everything inside that
Delta
bracket should be
N is
equals to
0.
1.
So in
Yeah,
this case
so
now, you
1
don't really
times
have to even bother yourself
4.95
here.
is 4.95. So that is how we got the Kp for that reaction.
Sixth topic, prediction of direction and extent of a reaction.
So let's talk about prediction of the direction and extent of a reaction. Like I said, prediction of the direction and extent of a reaction. Now you may want to ask yourself, what is this topic all about? If you can recall, when we talked about chemical equilibrium, I said one of the features of equilibrium is that a reaction is reversible. Is what I mean. All right. So now this particular reaction simply means it is reversible. So at a point in this reaction, the forward and the backward will move at the same speed. At that point, we say that reaction is at equilibrium. But before we attain that point, or after we must have attained that point, the reaction is not at equilibrium. Now, for us to be able to predict or to tell the direction of equilibrium reaction at a given point in time, we're going to be comparing two parameters, right? The two parameters that we're going to be comparing is the K equilibrium constant and the Q reaction quotient. So we're going to be comparing these two. Remember, equilibrium constants can be in terms of concentration or in terms of partial pressure. So if equilibrium constant is in terms of concentration, reaction quotient will also be in terms of concentration. If equilibrium constant is in terms of partial pressure, reaction quotient will also be in terms of partial pressure. So like I said, for us to be able to predict the direction of an equilibrium reaction, right, or a reaction that is reversible, we need to actually know the value of the K, and also we need to know the value of the Q so that we can compare. Now, like I said, in order for us to be able to predict the direction or extent of a reaction, we need to compare equilibrium constant and reaction quotient, right? Reaction quotient is a new terminology I'm bringing in, or we are hearing for the first time. But equilibrium constant, we have been hearing it as long as chemical equilibrium is concerned. Class, the two of them are very similar. In terms of definition, reaction quotients can be defined just like equilibrium constants. In terms of expression, the same thing. Now, one thing that differentiates or that separates both of them or that distinguishes one of them from each other is that we only talk about equilibrium constant when the reaction is at equilibrium, right? When the reaction is at equilibrium, that is only when we talk about equilibrium constant, right? Now, if a reversible reaction is not yet at equilibrium or it is beyond equilibrium, we talk about reaction quotient. So in other words, equilibrium constant is used at equilibrium, whereas reaction quotient is used before or after equilibrium. All right. Now, if you could recall also, I defined equilibrium constant as the ratio of the concentration of the product to that of the reactant, each raised to their coefficient, right? Now, that particular definition is at equilibrium. Now, how do we define reaction quotient? Class, look up. We say reaction quotient. Now, let's, just like we have Kc and Qc, if I'm asked for equilibrium constant, I'll define it in terms of Kc. Just like that, if I'm asked for reaction quotient, I'm also going to define in terms of Qc. So we say this, all right, so we said reaction quotient can be defined as the ratio of the concentration of the product to that of the reactant, each raised to their coefficient when the reaction is not at equilibrium. Emphasis on when the reaction is not at equilibrium. So if the reaction is at equilibrium, we are no longer going to be talking about reaction quotient, but instead it is equilibrium constant. So all those reactions, all those calculations we've been doing before now, it is assumed that, or it is presumed that those reactions were at equilibrium. So now we want to predict the direction of a reversible reaction at any point in time. If you start up a reaction now, the reaction will not just get to equilibrium. So let's say, for example, I have A plus B now. Our QC, that is reaction quotient, will be, we have concentration of the product, in this case is C, raised to the power of small letter c, concentration of this other one, all right. So this is actually the expression of reaction quotient, and of course you agree with me that this is actually, this is the same thing as the one for equilibrium constant, but you only write this when the reaction is not at equilibrium. Okay, now since we've actually established what reaction quotient is, now like I said, in order for us to be able to predict the direction of an equilibrium reaction, we need to compare the value of the reaction quotient to that of equilibrium constant. Now, in every question, if you're asked to predict the direction of the reaction, listen class, they must give you the value of the equilibrium constant. Like they must give you the value of Kc or Kp. And then you are to solve for either the QC, that is reaction quotient in terms of concentration or in terms of partial pressure. You're to solve for the Q and then compare the values. From the comparison, you can now make your decision. All right. So I'll say number one, if Q is less than K, that means if the value of the equilibrium constant, and when you compare the value of equilibrium constant and the value of reaction quotient, right, and reaction quotient is less than equilibrium constant, in that case we say the reaction is unsaturated and the direction of such reaction is reaction proceeds from left to right. That type of reaction, we call them forward reaction. So if you, after solving for your Q, the value you get is less than the value of K, you now say that reaction proceeds from left to right. In other words, the reaction is unsaturated. So the number two is if Q is equals to K, this reaction, the reaction is saturated. The reaction is saturated. So what is the direction of this reaction? The direction is that the reaction is at equilibrium. The reaction is at equilibrium. Now, when reaction is at equilibrium, it is neither moving to the left nor to the right. Remember, when a system is in equilibrium, the rate of the forward is equal to the rate of the backward. So it's not moving to the left, it's not moving to the right. It's just at equilibrium. Now, the third option is if Q is greater than K. Now, in this case, we say the reaction is supersaturated. We say the reaction is supersaturated. And what is the direction? Reaction proceeds from right to left, and that is backward reaction. So having said this, like I said, once they give you a question and you're asked to predict the direction of the reaction, you should always look out for the equilibrium constant, K. It will always be given, either in terms of Kc or in terms of Kp. So all you just have to do is that solve for your Qc or your Qp, depending on the parameters given to you. If they give you the parameters in terms of concentration, that is in a square bracket, that is concentration, you have to solve for your Qc. If they give you the parameters in terms of partial pressure, you have to solve for your Qp. And at the end of the day, you have to compare with your K. If after comparing here, you can now make your decision whether it is moving backward, forward, or is at equilibrium. All right. Now, let's look at this reaction here. Now, let's look at this reaction. They said for the reaction N2O4 giving us 2NO2, the Kc for that reaction, first thing first, I'll say solution. Kc for the reaction is 0.21. First, now the Kc for this reaction is this. At a point during the reaction, the concentration of N2O4 was this, and that of NO2 was this. Now the question says, is a reaction at equilibrium? Question mark. If not, in which direction is it progressing? So first thing first, you need to solve for your quotient, reaction quotient. Now using these parameters, they gave us this concentration at a point, meaning that it was not yet at equilibrium. Right? It could be before equilibrium or it could be after equilibrium, but it has not yet gotten to equilibrium. So I'll say my QC, remember, this is written, the expression of reaction quotient is the same thing as that of equilibrium constant. Ratio of the concentration of the product to that of the reactant, each raised to their coefficient. The only difference is that QC is used when the reaction is not at equilibrium, while Kc is used when the reaction is at equilibrium. That's the only difference. So in this case now, they said at a point, which means it has not yet attained equilibrium. So I'll say the product of this reaction is NO2. Now that's raised to the power of 2 all over N2O4. All right, so let's insert the values here. NO2 has a value of 0.55. Now this is squared because of this, and N2O4 has a value of 0.12. Now when you evaluate this, what are we going to get? Okay, so when you evaluate this, you're going to get 2.5. You're going to get 2.5, class. So you now say, now let's look at this. Our Kc was given to us to be 0.21, and our Qc from our calculation, we got it to be 2.5. So what is the final decision? You now say, since Q is greater than K, because our QC is 2.5 here, and our K is 0.21. So since Q is greater than K, the reaction is not at equilibrium. No, it's not at equilibrium. The reaction will proceed. Reaction proceeds from right to left, and that is a backward reaction, class. So if you want to write this in your notebook or in your answer script, right, you can just give them a well-detailed answer. After your calculation, you could say the reaction is not at equilibrium, comma, the reaction proceeds from right to left, which is a backward reaction. But you don't have to say which is a backward reaction. Once you say from right to left, in brackets, backward reaction. Okay, now let's look at the next question here. So in this question now, they said the Kc for this reaction, Kc for the reaction is 0.51. And they said predict in which direction will the reaction proceed to attain equilibrium if the initial concentration of hydrogen iodide, hydrogen and iodine are respectively 0.02, 0.01 and 0.03. Class, I believe we all understand that when they say respectively and then they proceed in giving us three values, it means that the first value corresponds to the first parameter here, the second corresponds to the second, and the third corresponds to the third here, right? But then what they gave to us here is mole, we are now told that all of them are contained in 2.0 liters vessel. Class, do you know what this means? I'll tell you. For you to solve for reaction quotient like we did here, we needed the concentration of this. Concentration is always a unit having unit of molar or mole per liters. So if they give me mole and they give me volume, I need to convert mole and volume to molarity. That's molar concentration. And how do I do that? I'll say concentration of HI equals to mole HI all over volume of the container. Now the mole of HI was the first one here. So the first value here is going to be that for HI because they use the word respectively. Respectively means three of these values, right? The first one goes to the first, the second goes to the second, and the third goes to the second. So we have 0.02 mole all over 2 liters. Class, the volume has to be in liters or dm cube. So if they give you volume in any other unit other than liters or dm cube, you have to convert before you can use it here, because molarity is always having a unit of mole per liters or mole per dm cube. All right. So when we solve this, the first one, this gives us 0.01 molar, and that of hydrogen. The mole of hydrogen, I don't have to rewrite this formula again. The mole of hydrogen is 0.01. So this is 0.01 divided by 2. Now the answer there is 0.005 molar. And that of I is 0.03. 0.03 divided by 2. So this becomes 0.015 molar. So we have succeeded in getting the equivalent in terms of molar concentration. So we can now proceed to solve for their reaction quotient, right? So that we can now compare with the equilibrium constants given to us. All right, so we say QC for this. Now this is the reaction. Now the product, the concentration of the product divided by that of the reactant, each raised to their coefficients. So this is the product is HI and the reactant is H2. So let's input the values. Concentration of HI is 0.01 all raised to the power of 2. Concentration of HI is H2 rather is 0.005 times I2 is 0.015. Now when you carry out this calculation, our QC becomes 1.33, guys. So the next thing you're going to do here is to compare. Now KC is equals to 0.51 and QC is equals to 1.33. So what can be said here is very obvious that QC is greater than KC. Very obvious because QC is 1.33 is greater than 0.51. So in this case now, once QC or Q is greater than K, the reaction proceeds from right to left, just like what we did here previously. So this reaction, the question says, predict in which direction will the reaction proceed to attain equilibrium. Backward reaction. That is from right to left. Okay, so that is it for this particular section. All right.
7th topic, heterogeneous equilibria.
Now, basically, what does it mean for something to be heterogeneous equilibria? Let me show us an example. If I have A, we have gas, plus I have B, we have gas, and I have C, we have gas. Class, look up. If you look at this, the state of these three species are all gases, gases, and gases. So this type, we call them homogeneous equilibrium. Now, this is not something to be worried about. This, when something is homogeneous, it simply means that all the states are the same. So, but when we are talking about heterogeneous, I'll tell us shortly. Now, in homogeneous, it's either they write out all the states, like in this case, or most cases, they will not write anything at all. Right? So anytime you don't see anything at all, take it to be gas. Right? Gases are the ones that are commonly ignored. Right? If it is a gas, they can ignore it. All right. Now, heterogeneous simply means, now this example of heterogeneous. So if I have something like this, let's say, example, I have A gas plus B liquid, C solid. Class, if you're to write equilibrium constant expression for heterogeneous equilibria, now this is, please listen and listen very carefully. Liquid and solid does not take part in equilibrium constant expression. Never. Liquid and solid does not take part. The only two state of species, or the only two state of species that can take part in equilibrium constant expression is gas or aqueous. These are the two that takes part in equilibrium constant expression. That is for Kc. You understand? Now, for Kp, mostly for Kp, whenever you're writing Kp, remember Kp is partial pressure equilibrium constant. If you're writing for Kp, it's mostly gases that is allowed to be written for Kp. But whenever you're writing for Kc, gas or aqueous are allowed to be represented or to be shown. Now let's look at this. If I write for this first one, this is going to be concentration of C raised to the power of C divided by concentration of A. Right? Now for the second guy, this is a solid and this is a gas. So I'll say, class, anytime you see a state of a reactant or a product that is not a gas or aqueous, put it to be 1. Put it to be 1. So here is 1 because this guy is a solid times, because this is a gas, so I'll express it here, all over. A is a gas, so I'll express it times. B is a liquid, I'm not going to express it. So at the end of the day, this is D all over A.
8th topic, Le-chatelier principle and factors that affect equilibrium.
All right, so we have the principle that is guiding reaction at equilibrium. We call that principle Le-chatelier principle. Now, what is Le-chatelier principle? It states that if a system in equilibrium is disturbed, right, the equilibrium will readjust itself so as to annul the effect of the disturbance. Now, when we talk about disturbance, right, we're not talking about noise, no. Now, the disturbance can be in the form of so the disturbance, when we talk about disturbance, this is what we mean. The disturbance can be in terms of change in concentration or change in pressure. So let's talk about concentration. How does concentration affect a system at equilibrium? Let me give us an example. Let's say number 1. The first one we want to talk about is effect of concentration on equilibrium. How does change in concentration affect equilibrium position? Now pay attention. I want to draw a diagram or a diagrammatic representation so that we understand this better. Class, imagine we have something like this. Now, I just created an imaginary equilibrium system. Now, this is assumed to be two tanks that is connected to each other at the bottom. Class, you all agree with me, just from by mere reasoning, that if you put water here, after some seconds, the water will split itself and be on both sides equal amount. So if I come here and I empty 10 liters of water on one of this side, right? After some seconds, the 10 liter of water will share itself into two. 5 will be retained here and 5 will move over to this side. In this case now, you have created an equilibrium. At every point in time, there will be same water level on both sides of the tank. Now, this is a concept that is being applicable, that is used in borehole tanks, overhead tanks in our houses. So at every point in time, same level of water would be. So if I empty 20 liters of water here, after some seconds, the 20 liters of water will split itself into two. 10 will retain in this, 10 will be retained here, and 10 will actually move to this side. Class, what do you think would happen? Let's assume I have 10 liters of water here and also have 10 liters of water, right? What do you think will happen if I take out 2 liters of water from this side? If I take out 2 liters of water, this will no longer be 10 liters. This will now become 8 liters. Class, listen. This, I have disturbed this equilibrium system now by taking out water from this. And this is what is going to happen. This side will no longer be 10 liters. No, for the fact that you have reduced the volume of this water from 10 to 8 by removing 2 liters here. Now, you have disturbed this equilibrium. So this equilibrium is going to readjust itself in such a way that these 10 liters will release 1 liters of water. So this was initially 10. This will now become 9. And it will release 1 liters of water to this side, so that here now becomes 9 liters. By so doing, a new equilibrium has been established, right? But that is not where I'm heading to. Where I'm heading to is, which direction did the water flow towards to replenish the one that was taken off? Class, the water was taken out from here, all right? Now, water now flowed from the left coming to the right to stabilize the equilibrium that was disturbed. In other words, anytime a product, the concentration of a product is decreased, if you decrease the concentration of a product, listen, if you decrease the concentration of the product, equilibrium will move from left to right to adjust or to annul the effect of that disturbance. So removing water from this product is equivalent to decreasing the concentration of the product. I believe you're following. So two things can make water flow to the right-hand side. It's either you reduce the water level on the right or you add more water to the left. Because if you add more water to the left, that excess water will be splitted and some parts shifted to the right. Right? So therefore, I'll say increase in concentration of reactants and decrease in concentration of products. Let's say increase or decrease in concentration of products shifts equilibrium to the right. That is from left to right. So that is forward reaction and vice versa. So what is the vice versa of this? Number 2, vice versa, opposite of this means if reducing the concentration of the product or increasing the concentration of the reactant and shift equilibrium to the right, what can we do to shift equilibrium to the left? opposite of this. So I will now say decrease in concentration of reactants or increase in concentration of products. Now, basically opposite of this. So once you know one of them, just take the other as the opposite. Okay, now this is equilibrium will shift to the left. That is backward. Class, please, I just remember something now. This disturbance, please add number 3, change in temperature, because temperature also has effects on equilibrium. Let's come back to this. So, but these are not the ways question can be asked. No. Now, this is mainly for those persons that are writing JAM. So, for those persons in the university or tertiary institution, how can they ask questions based on this? Now, let's look at this question. They said, use equilibrium reaction to predict the effect of removing CO2 from this equation. Class, CO2 is on the product side. Just imagine what we did here previously. What will be the effect of removing water from the product side here? Because let's assume CO2 is on this container and this is on the other container. So once you remove CO2 from here, this guy will have to produce another CO2 until he's no longer able to produce CO2. So if you keep removing water from here, this guy will keep, if you remove water from here, this guy, the left hand side, will keep replenishing the water until this guy has no water again to replenish. In that case now, you have terminated the equilibrium reaction. So here, removing the product, once you remove this product, this calcium carbonate will be forced to produce another CO2 to be able to maintain this equilibrium. The more you're removing this guy, the more this guy is releasing more CO2 until it's no longer able to produce CO2. So what will be the effect of removing CO2 here? Use the equilibrium reaction to predict the effect. Removing CO2, shifts equilibrium to the right. So if you're removing CO2, it shifts equilibrium to the right. And that is the concept behind that. Okay? All right. So we are done with effect of concentration on equilibrium. So let's look at effect of pressure or effect of temperature. So I'm going to just talk about that of pressure and temperature at once. On equilibrium affects the direction. Let me tell us this. Class, from Boyle's law, pressure is inversely proportional to volume. This simply means that if you increase pressure, volume decreases. If you decrease pressure, volume increases. Inversely proportional. If one is going up, the other one has to go down. So, if you increase the pressure of an equilibrium reaction, listen, the direction of the equilibrium will be towards the side that has lesser volume. So increase in pressure of an equilibrium reaction shifts equilibrium to the side that has lesser volume, because if you increase pressure, volume decreases. So for a reaction that are gases, right? For this particular effect of pressure, pressure only affects gaseous reactant and products. So let's say, for example, I have N2 plus H2, 3, 2NH3. Now this is a gas, this is a gas, and this is a gas. Class, the volume of this gas can be seen to be the mole. So this is 2 volume, which is same thing as saying 2 moles on the product side. Now the reactant side has, this is a gas, so 1, this is a gas plus 3. So this is 4 moles, which is seen as 4 volume. Good. Now, if I increase the pressure of this reaction, increase in pressure will shift the equilibrium to the side that has smaller volume, because increase in pressure leads to small volume. And which side? We said this substance, for pressure to actually act on them, they have to be gases. If they are liquid or solid, you take it to be 0. If they are liquid or solid, you take their mole to be 0. It is not counted. Pressure has no effect on them. So here, for this reaction, the mole of the product is 2, which is equivalent to the volume. Here, you add up the mole of the reactant. This is 1 and this is 3. 4 mole or 4 volume. So if you increase in pressure, class, we will shift equilibrium to the side that have lesser volume. And which side is that? The product. Increase in pressure shifts equilibrium to the side that has lesser volume. And vice versa. So let's use this equation and explain this. If I should increase the pressure of this reaction, class, the product has 2 volume, which is 2 moles. The reactant has 4 volume, which is 4 moles. So looking at this, the product has lesser number of volumes. So if you increase the pressure of this reaction, equilibrium will shift to the right because the right side has lesser volume. Alternatively, or conversely, if you decrease the volume, decrease in pressure leads to increase in volume. So if you decrease the pressure of this reaction, what happens? Equilibrium shifts to the side that has more volume. So increase in pressure leads to the side that has less volume, right? Decrease in pressure leads to the side that has more volume, and that is that for pressure. So in this question now, if I decrease the pressure of this reaction, it will move to the side that has more volume. Okay? Now, what if both sides of the reaction have same number of mole or same volume? What if the left-hand side has 2 moles or 2 volume, for example, and the right-hand side also have 2 moles? In this case, pressure has no effect on such reaction. Class, when the sum of the mole of the gaseous reactant is equal to the sum of the mole of the gaseous product. In other words, the mole of the reactant, the gaseous reactant, is the same as the mole of the gaseous product. No side is small or no side is higher in terms of moles. In this case, pressure has no effect on it. All right? So let's assume, for example, I have something like, let's say, H2 plus I2 giving me 2Hi. Now look at these two reactions. The mole of this product is 2 mole, which is 2 volume. This is 1 and this is 1. So 1 plus 1 is 2 mole, which is 2 volume. The left hand side is having, the reactant side have 2 moles. The right hand side is having 2 moles. So if you increase the pressure here, there is no side that is lesser in volume. There is no side that is higher in volume. So pressure will not affect such reactions. Reactions where the number of moles of the gaseous reactant is same as the number of moles of the gaseous product. Pressure has no effect on such reactions. Okay? Okay. Now let's look at the last but not the least. Alright, so let's look at effect of temperature on equilibrium reaction. Class. Now, unlike the previous two, concentration and pressure, unlike the previous two, that is the concentration and the pressure, where they just told us increase in concentration or decrease in pressure and the rest of them. In the case of temperature, you have to specify, you have to pay attention if the reaction is endothermic or exothermic. Because reaction can either be endothermic or reaction can be exothermic, right? Both of those two reactions have different way they react when you increase temperature. So I'll say for endothermic reaction, how will I know if a reaction is endothermic? If the delta H is positive. delta H is greater than 0. That is, delta H is equals to positive. For exothermic, delta H is less than 0. That is, delta H is negative. Class, listen and listen very carefully. I don't intend to spend so much time. Endothermic reactions are reactions that requires heat for them to proceed forward. Every chemical reaction proceed forward. There is no chemical reaction that you react and it start going backward. No. If you react two substances together, they move forward to produce a product. Do you understand? So whether it is exothermic or whether it is endothermic, no, all of them will always go forward. Now, how does temperature affect those reactions? And listen very carefully. Endothermic means I need to gain heat for me to proceed to form a product. So for endothermic reaction, if you increase the heat, it will accept it because it needs heat to go faster. Endo means it needs heat, exo means giving out heat. So for endothermic reaction, they absorb heat or they gain heat. Imagine something that requires heat and you now increase the temperature. Increase in temperature means you're increasing the heat. So for endothermic reaction, increase in temperature class shifts equilibrium forward because that reaction normally is moving forward. So you now increase the temperature, it will make the forward to be faster. So increase in temperature favors forward reaction. Obviously, once increase in temperature favors the forward reaction, that is from left to right, you know what decrease in temperature will do to that guy? Take it backward. Decrease in temperature will favor backward reaction. Now that is for endothermic. Now let's talk about exo. For exothermic reaction, exo means I'm losing heat. I want to go forward, but I don't need heat. I need to lose heat to go forward. Imagine me now, for me to move forward, I need to lose heat. So anything that will make me lose heat will propel me forward. I don't know if I'm communicating. Exo means I need to lose heat to go forward. So decrease in temperature, if you reduce the temperature of this exo, that means you're removing heat, you help this guy to go forward. Unlike the one of endo that needed heat to go forward. So for exo, for me to go forward, I need to lose heat. So I'll say decrease in temperature for exo favors forward reaction. So I repeat, every reaction needs to go forward. For an exothermic, I need to lose heat for me to go forward. So if you decrease my temperature, that means you're removing the heat. You help me go forward faster. So decrease in temperature favors a forward reaction. And obviously, we know that if you increase the temperature, you favor the backward. So that is that for chemical equilibrium. So if you actually follow this lecture from the beginning to this point, congratulations, you've completed every section of Chem 1-3 chemical equilibrium topic. You can go ahead to smash your past questions, right?
The other part of equilibrium will come under a new chapter, Solubility Product Constant, KSP. Subscribe to our channel by clicking on the button below to avoid missing out. And see you in the next video.